Well, welcome to our next lesson on similar polygons. Our objective today is to be able to identify and apply properties of similar polygons. And similar figures are figures that have the same shape, but they're not the same size. And our abbreviation for is similar to is this little symbol right here, this little twiddle symbol. I don't know what the technical name for that is, but that's what we'll call it. And two polygons are similar if their corresponding angles are all congruent and if the lengths of their corresponding sides are proportional. So symbolically we would say this. We would say angle A is congruent to G, B is congruent to H, C is congruent to I, D is congruent to J. All of the angles must be congruent, and then their corresponding sides must be proportional in length. So they don't have to be the same length, but they all must share the same ratio. And this proportion right here with all of these side lengths is called an extended proportion, and that's a review. We learned that in our last lesson. A scale factor is the ratio of corresponding measurements of two similar figures. So, for example, we have these two triangles right here, ABC and XYZ, and the ratio of the corresponding side lengths, if we take the ratio of BC to YZ, that would be 20 over 8, which is the same as 5 over 2. So our scale factor in simplified form is 5 to 2. Now when we use our scale factors, we want whole numbers. We don't want decimals, so we wouldn't say it's 2.5 to 1. We're going to leave those as whole numbers in the most reduced form that we can find. So here's a problem for us to try. We have triangles MNP is similar to triangle SRT. Now just like when we had congruent triangles, the order of the letters tells us the corresponding sides that are similar. So what are the pairs of congruent angles? We could tell that even if we didn't have a picture, we could tell by the order of the letters. So just by looking at the letters, we know angle M is similar, or excuse me, congruent to angle S. Angle N is congruent to R, and P is congruent to T. So we could also write an extended proportion for the ratios of the side lengths just using our similarity statement. So just looking at those, we could say that side MN would be similar to side SR, NP would be similar to RT, and MP would be similar to ST. So they all would have to share the same proportion. Here's another one. Why don't you go ahead and try this one on the got it on the top of the page here. What are the pairs of congruent angles? And what is the extended proportion for the ratios of the lengths of corresponding sides? Go ahead and pause the video and write those statements out, and I will show you the answers when you come back. All right, hope you gave that a try. Here are your congruent angle statements. D is congruent to H, E is congruent to J, F is congruent to K, and G is congruent to L. And your extended proportion should look like this. DE goes with HJ, EF goes with JK, FG goes with KL, and GD goes with LH. Here's the second problem, determining similarity. Are these two polygons similar? If so, we want to write a similarity statement and give the scale factor. So first of all, we would have to identify the pairs of congruent angles, and it looks like we do have all four pairs of congruent angles are congruent. And then we would have to compare the ratios of the lengths of the corresponding sides to see if all four sides have the same ratio of their lengths. So when we look at those, we're getting different ratios of the sides. And since we have different ratios, we can conclude then that these definitely are not similar. Okay, because we didn't get the same proportion for all of those sides. Are these polygons similar? If they are, write a similarity statement and give the scale factor. So first of all, identify the pairs of congruent angles, and it looks like we do have 3 pairs of congruent angles, and then comparing the ratios of the corresponding sides. So here are the ratios of the corresponding sides. They all turned out to be the ratio 4 to 5, so we do have similar triangles, and there is our similarity statement. Triangle ABC is similar to triangle DEF. Here's one for you to try. Actually, there's 2 for you to try. Determine whether or not the polygons are similar. If they are, write the similarity statement and give the scale factor. I'll give you the answers when you come back. Alrighty, hope you gave that a try. Here we go. These are our angle congruent statements. Now all of these are 90-degree angles, so this is a little bit tricky because you have to look at also the sides to figure out which angles should go correspondingly. So I chose K is congruent to X, L congruent to Y, M congruent to Z, N congruent to W. But then when we go ahead and write our proportionality, our extended proportion, we find out that we do not have the same proportion for our sides. So 15 to 20 is not the same as 15 to 10. So therefore, we do not have similar polygons in this instance. Letter B, we go ahead and write our angle congruent statements and our extended proportions. And then when we go ahead and plug in the values that we have into our extended proportions, we find out that they all have a ratio of 2 to 1. So that was the one thing I didn't write on here is our scale factor. So let me go ahead and write that in. Our scale factor on this one is 2 to 1. Alright, problem number 3 says, using similar polygons. We start out where the statement tells us they are similar polygons. What is the value of x? Well, we can go ahead and write a proportion since we have that the polygons are similar. So we're going to say F is to G as B is to C. Those are corresponding sides. And E is to D as A is to D. So now we can substitute those values. And then using our cross products, we end up with a value of x being 5. So your turn to try, using the same problem, same diagrams, find the value of y. I'll go ahead and pause the video and we'll give you the answers when you come back. Alright, hope you gave that a try. I'm going to try to go ahead and pull this without getting rid of my figures up there. So here's what you should have. I'll put it up here. It's easier to see. So in our polygons, our ratios are EF is to AB as DE is to DA. So we have Y is to 5 as 6 is to 9. And then using cross products, we get 9Y is 30. And Y works out to be 3.3. Problem number 4 using similarity. Your class is making a rectangular poster for a rally. The poster's design is 6 inches by 10 inches wide, and the space allowed for the poster is 4 feet high by 8 feet wide. What are the dimensions of the largest poster that will fit in that space? So first of all, we have to determine whether the height or the width is going to fill the space first. So our height, 4 feet, is 48 inches. And we have 6 inches is the dimension that we have right here in our design. So if we divide 48 by 6, that allows us to magnify that 8 times. But if we look at our width, 8 feet is our maximum width, which is 96 inches. And our poster is 10 inches. And that allows us to to magnify by a factor of 9.6. But we have to magnify the same dimensions proportionally, so we're only going to use 8 times. Okay, so the greatest height is going to be 48 inches, and then we want to find the width using that magnification factor or that scale factor. So using our corresponding sides, we're going to say our 6-inch height is to the 48-inch height. Remember, 6 is what we actually have for the poster that we're making, and the poster size is 48 inches. Our width is 10 inches and we want to know what the new width will be. So using our cross product, 6x is 480 or x is 80 inches. So the largest poster we can make is 48 inches by 80 inches, and in terms of feet it would be 4 feet by 6 2/3 feet. In a scale drawing, all the lengths are proportional to their corresponding actual lengths. The scale is the ratio that compares each of the lengths in the scale drawing to the actual length. You're very familiar with scales if you've ever looked at a map, and those are often different units. So your scale might say something like 1 centimeter is 50 kilometers, or an inch is 100 miles, or whatever. Okay, the point is that those are probably going to be different units, and we can use proportions to find what our actual dimensions would be from a scale drawing. So here's an example where we have a scale drawing of the Golden Gate Bridge, and the distance between these two towers right here has been measured, and we want to know what the actual length in real life of that main span of the bridge would be. Well, this length of the main span in the scale drawing is 6.4 inches. They're telling us that's what they measured with a ruler on the drawing is 6.4 centimeters. We're going to let S represent the main span of the bridge, and we're going to set up a proportion to figure out what that is in actual life, in real life. So 1 is to 200, that is our scale, okay, that was given in the drawing down here. 1 centimeter is 200 meters, so pay attention to your units. And then we measured 6.4 centimeters, so that's going to go on the top, 1 centimeter and 6.4 centimeters, 200 meters to S meters. And then if we use our cross product, we get S is equal to 1,280 meters. That's all for this time. We'll see you next time.